Alright, so what is up there is mostly things that we went over in the isotopes Poggle. We want to make sure that you know how to read a periodic table because you're going to be using it a lot through the rest of the year. So at the top, we've got the atomic number, which we learned is defined as the number of protons, and this is always a whole number. So most of the time, periodic tables will put this number at the top. I have seen some that have not necessarily put it at the top, so if you're trying to figure out which number is which, figure out which one is consistently a whole number in every box, and that's your atomic number. All right, just going down the box. The symbol, do make sure you write them correctly. You'll be getting your list of the ones I expect you guys to know pretty soon. Maybe tomorrow, maybe Monday. But make sure that the first letter is capitalized, and if there's a second letter, that you write it in lowercase. And it needs to be obvious. If you write them both capital letters or both lowercase letters, I am going to mark it wrong. Okay? There should be a size difference between the first letter and the second letter. Alright, and then the bottom one is your mass number. Sometimes they call it atomic mass, sometimes they call it atomic weight, even though that's not technically correct. But this is usually a decimal number. If you look up at the periodic table that is now up on the wall, you'll notice there are some of them that are not a decimal number. There's several of them that are whole numbers. And what do you notice about the ones that are whole numbers? What are they in? They're in parentheses. Okay? All of those things that are in parentheses, that is not the isotopic abundance weighted average. It is actually the mass of the most stable or longest lived isotope. So all of those that you see up there that have their mass in parentheses are radioactive. And so every element after 83 bismuth, starting with polonium, 84, all of them are radioactive. Now there are two that occur before that are radioactive. That would be technetium, which is 43, and then promethium, which is 61. Also, if you're just looking up there, you notice that there are some of them have white letters with black outline. All of those are man-made elements. They're synthetic. They do not naturally occur on Earth. You might find them naturally somewhere else in the universe, but not here. And then the red ones are all gases. The two blue ones are naturally liquids, and everything else that's in black is naturally a solid. So, all right. There were a couple of questions towards the end of your isotopes Poggle where you were trying to figure out which isotope was most common. Remember that the one that's most abundant or most common, the average on the periodic table is going to be closest to it. So like there was a question about boron, that it only has the two isotopes, 10 and 11. And it said, well, which one's most abundant? Well, since boron's average atomic mass is 10.811, 11 is a lot closer to that, so you know that boron 11 is more abundant. All right, one last thing with the stuff up there. The mass number or atomic mass has a unit. And you saw this in the Poggle, but I don't think they really talked about it too much. The unit for atomic mass is literally atomic mass units, AMU. And how much matter is that? Well, scientists arbitrarily decided that it was going to be equivalent to 1/12 of the mass of a carbon-12 atom. So, just FYI. Okay, now that everybody in class has gotten it written down, we're going to practice getting the numbers of protons, electrons, and neutrons. And keep in mind, when an atom is neutral, the number of protons and electrons is equal because they cancel each other out. So for right now, all we're going to be looking at is neutral atoms. We'll talk about those that are not neutral later, and you'll have to do something about the number of electrons with those. But I'll let you guys pick the first 4 elements that we do, and we'll do them together, and then I'll pick the last 4 and give y'all some time to do those on your own. So pick some elements that did not appear in your Poggle already. You can call out the symbol if you don't know what the name is. So, give me some. Aluminum. Okay. Oh, I need to change that back from pink to black. Alright, so aluminum. What's another one? Pick something, y'all. Bromine. Okay. Pick another one. Iron, okay. One more. Zinc. Alright. All with the metals. Okay, so we have to locate them on the periodic table. Aluminum is in column 13, and it's actually also atomic number 13, so that means it has 13 protons and 13 electrons. However, is there a number up on the periodic table that we can simply write down that is the number of neutrons? Yes, no? Murmurings of no, because they're afraid that they're going to die if they're wrong. You have to calculate the neutrons. In the POGL, you defined the mass number as protons plus neutrons. Well, you need to subtract the mass number and the atomic number. So you're going to round the mass number to a whole number. So for aluminum, that would round to 27. And then we're going to subtract the atomic, 13. So that's going to give us 14 neutrons. Okay? Alright, let's do the next one. Did y'all find bromine on the periodic table? It's one of the two blue ones because it's one of the only two elements that naturally exists as a liquid. So how many protons does it have? 35, because it is atomic number 35, which means also has 35 electrons. So that mass would be rounded to 80. And we'll subtract 35, so 45 neutrons. Yes?
Can I have Cameron back to check out, please?
He's on his way.
Thank you.
Alright, so iron, did we find it on the periodic table? Iron is right in the middle. Fe. It is element number 26. So 26 protons, 26 electrons. We will round that mass to 56. Subtract 26. So we have 30 neutrons. Yes, ma'am. Alright, well, the mass up there is 55.845. So that would round up to 56. Yeah. Just looking at that first digit in the decimal, tell you if it needs to stay the same or round up. Alright, and zinc. Protons, how many? 30. So 30 electrons. So what would we round the mass to for zinc? Yeah, it'd be 65 because it's 65.39, so it wouldn't round up. So 65 minus 30 gives us 35. Okay? Alright, now I'm going to give you some, let's see. Let's do Meitnerium, silver, radon, and titanium. Okay, so we will pause and let y'all work on those. Alright, so everybody in here has finished their calculations. So, Meitnerium, named for Lisa Meitner, one of the earliest famous female chemists. She worked on nuclear stuff in Germany. So that's why she got an element named after her. So that element is 109. So that means 109 protons, 109 electrons. Its mass listed up there is 276. So we will subtract 109 from that. And that gives us 165. Is that right? I did not calculate myself. Wait, no, it doesn't. Does it?
67.
Yeah. I was like, that didn't look right. Y'all calculated it. Give me your answer. Instead of waiting for me to say it. Alright, so silver, Ag, element 47. Alright, what did you round the mass to? 108. So 108 minus 47. So that's 61. Alright. Change to blue. RN, radon. Radioactive gas. If you have a basement, you may have a radon detector because this gas seeps up out of the ground and can, like, poison you and kill you. Fun times. So this is element 86. So it has 86 protons, 86 electrons. The mass we don't have to round because it's already a whole number. So 222 minus 86 gives you what? 136. Yeah. All right, and then titanium. Which they use for all kinds of stuff because it's lightweight and it doesn't react with much. So that's element 22. And then what did you round the mass to? 48 minus 22, so that's 26. Okay? Yes, good. Questions? Do we notice anything about the relative number of neutrons to protons? Some of them it's about the same. Some of them there's a whole lot more neutrons. What do you notice about the ones that have a whole lot more neutrons than protons? Yeah, these are larger atoms. So what happens is that the bigger and bigger, the more protons you have, the more neutrons you need to hold the nucleus together. Because neutrons act like glue. Just remember, protons are positive. Do two positive charges want to hang out next to each other? No, not really. So, and you may have remembered mention of the strong force in the video series that we watched, because that's what holds the nucleus together. But there's only so much strong force can do versus the repulsion of protons, especially when they start getting bigger, because the farther away they are from each other, the more the repulsive force wins, and the strong force can't help it. So if you add neutrons into the mix, it does not add any repulsion, but it adds to the strong force attraction. So that's what makes it stable. So we'll see that mentioned in the little video that we're going to watch tomorrow. All right. Let's move on to average atomic mass. All right, this is something you're going to have to calculate on the test. Okay, you need to know how to set it up. I'm not going to give you that formula. Okay, why do I not give you the formula? I'm not really big on memorizing formulas for the most part, but this one is integral to you understanding what average atomic mass means. Because it's literally, if you know what it means to be an abundance-weighted average, like the way we calculate grades, then you should be able to set it up. Now, if you remember from the POGL, there was a couple of ways to set that calculation up. I'm giving you this one simply because from experience, if I tell you to go ahead and convert the percentages into a normal number, you will either forget or you incorrectly convert things that are less than 1%. So if you do this version of the formula, you tend to get the answer right more often than not. And then make sure that it has a unit. They didn't really talk about the unit for atomic mass so much in your POGL like you saw it, but I don't think they really explained it. So again, that's the AMU, atomic mass unit. Sometimes students want to put AAM as the unit because you see me abbreviate average atomic mass as AAM, but that's not the units. It's AMUs, literally atomic mass units. Okay? So I'll give y'all a moment to write the problem down. Tomorrow when we do practice problems, I'm going to have the text of the problems on a sheet for you so you don't have to write it all down. But since we're just going to do this one, you can write it down. So, pausing for a moment. Alright, so everyone here has had a chance to write down the problem. So, let's pick this apart. So, the problem is talking about unknown element X, and we know it has two isotopes. So let's write down the information that they gave us about the two isotopes. So X14 has a mass of 14.00307 AMU. So I'm going to kind of make myself a little table here. And then they gave us the percentage, 99.63%. And then the isotope X15 is 15.00011 AMUs. Okay, they did not give us the percentage for X15. What do we do? Come on, use your brains. What do you know about percents, Connor?
There's only 100% so you can subtract it.
Exactly. Your percentages have to equal 100% because percent literally means per 100. So just subtract what you've got from 100. See, now we have all the numbers that we need to plug into the formula that we had earlier. Okay, so let's see. I gave you the percent first. Really and truly, it doesn't matter if you do the percent or the mass first because multiplication is commutative. You get the same answer whether you do it, 6 times 3 or 3 times 6. And then divide all of that by 100. Okay, so let's talk a little bit about calculator habits. Your calculator is only as smart as you are, which means it's going to do what you tell it to do. So if you don't tell it to do the correct order of operations, you're not going to get the correct answer. So to do that, use parentheses. So when I'm punching in to get the answer to this problem, I'm going to do open parentheses, 99.63 times 14.00307, close parentheses, plus, open new parentheses, 0.37 times 15.00011, close the second set of parentheses, and then hit your enter or solve or whatever the button is. So you should have 1400.675905 in your calculator. Now, divide that by 100. Now you have something that sounds more reasonable. 14.067 blah, blah, blah. And I'm going to write that down. Change this to pink. So 14.00675905. Now, that is your calculator answer. Always do a reality check when you're doing these problems. Okay, you know that if you've only got these two isotopes and their masses are 14 and 15, the average should be somewhere around those two numbers. So if you're getting an answer that's way too big or way too small, that means you did something wrong. You miscalculated something, you put something wrong in the calculator, go back and check your work, do it again. Okay, so always do that little reality check. All right, so next question is, do we have to write all that? No. You have to round your answer. How do I do that, Ms. Taylor? Well, there's a rule for that, and this is where sig figs come to haunt you for the rest of your life. Okay? Whenever you multiply or divide when solving a calculation, you are going to round your answer so that it has the same number of sig figs as the number given with the least. Long sentence. In practice, okay, the 3 numbers in blue are the numbers they printed for you in the problem, right? Okay, so which one of those 3 numbers has the least significant digits or figures? Mass, or percent? The percent. The percent only has 4 sig figs versus a whole bunch. So that means we want to round the answer to 4 sig figs. Okay? So when we look at what we got in the calculator, we're looking at that part because we read numbers left to right. So the question becomes, do we put 14.00 or do we need to round that 0? We should round the 0 up. So the correctly recorded answer for this is 14.01 AMU. So if you multiply or divide in a calculation, round to the least number of sig figs in the problem. You may be going, but what about the 0.37%? That was not given in the text of the problem. That's something you solved for in the course of the problem. So whenever you're trying to decide sig figs, look at the text of the problem and look at the numbers. Now, you still have to be careful that if they give you a number that is something counted or a conversion factor, remember those things have an infinite number of sig figs, and that's not going to affect how you round your final answer in a calculation. Also, there's a separate rule for adding and subtracting, but when we actually need to use it, we'll go over it. So, don't worry, we're going to practice this a whole bunch more, and I'm going to drill it into your brains by repetition. So, any questions from this problem we need to go over? No? No, and it's almost time to go. Okay. So, those of you who are watching at home, good afternoon.